Now we'll begin the basics of deformation and recrystallization texture. I'm going to start with the definition of texture. Texture defines the orientation distribution of grains in a polycrystalline material with respect to some macroscopic axes. Let's say that again. Crystallographic texture describes the orientation distribution of grains in a polycrystalline material with respect to some macroscopic axes. For example, the macroscopic axes in rolling would be the rolling direction, the transverse direction, and the normal direction. We can define a random texture as a material that contains a random set of grains. A material that has a strong texture would have many grains that have a similar orientation with respect to the macroscopic orientation. We define the strength of that texture quite easily. For example, I find one grain at a certain orientation with respect to the macroscopic axis. In theory, if I have 1,000 grains, there may be only 2 grains that have that orientation. But when I look at the material, I see that there are 10 grains that have that similar orientation. So in that case, I have 10 divided by 2 multiples of random intensity. So I have a texture strength of 5. Okay, so the first thing we have to note is deformation textures. In deformation textures, we effectively, in plastic deformation, apply a change in shape. We apply strain. To accommodate this change in shape, we need dislocation motion or plastic slip. That means plastic glide on a crystallographic plane. If we have plastic glide on a crystallographic plane, we automatically generate lattice rotation. So when we have plastic deformation, we also have lattice rotation. That means that our crystal rotates. In polycrystalline deformation, we have to have 5 slip systems operating to accommodate the plastic strain. That means we have 5 different slip systems that are independently rotating the orientation of our grain. Therefore, as we deform the material, our individual single grains within our material rotate to accommodate the plastic strain. We also have another interesting issue. Because our grains are orientated in different ways, we end up with a scenario that plastic deformation will be harder in certain directions than others. The first way that we can define this is looking at the so-called Langford coefficient, or sometimes known as R. Imagine I am pulling my sample in a tension test in the direction sigma y. As I pull it, the material is going to contract in the direction epsilon x and contract in the direction epsilon z. So effectively I have a contraction strain epsilon x in the width direction and a contraction strain in the thickness direction epsilon z. We then define the ratio, the Langford coefficient R, as equal to the ratio of the contraction strain in the x direction divided by the contraction strain in the z direction. Now a really important point then is, if we wanted to have a high strain to failure, what we would want to have is the material not thinning very quickly. If it thins very quickly, then the cross-sectional area reduces rapidly. So we need to have a very high R value to get a very high elongation to failure. If I had a random set of grains, R would be equal to 1. But by having a non-random set of grains, such that there is very little plastic strain in the Z direction, I can get a very high value of R, whereas if I had it the other way around, I could get a very low value of R. Okay, so it's very important, this concept. So ideally, I want to have a scenario of a value of R greater than 1. If I have a value greater than R greater than 1, then I must have a texture which makes sure that there's virtually no strain in the Z direction. This also has an impact on the yield stress behaviour of the material. Notice on the right hand side we have a yield surface equivalent to von Mises for different values of R. And you can see as I increase the value of R, I suddenly get much higher strength in certain directions compared to others. So I can see that by manipulating the crystallographic texture, I can change the formability, i.e. the ability to elongate to failure, and I also change the in-plane properties. I get yield stress and isotropy, i.e. certain directions have higher strength than other directions within the plane. And of course, this has a massive impact on sheet metal forming operations. In this case, because I have a non-random distribution of grains, and such that I have a variation in yield strength of the material in the plane, when I do a deep drawing operation, I end up with a scenario known as earing. You can see in this case, I have material where it was very easy to deform in this direction and much harder to deform in this direction. That meant that I got a non-uniform surface. That means I have to cut this off, therefore wasting a lot of material. The other thing though, of course, is it's going to be much thinner in this area than in this area. So I'm having a waste of material here as well. So the key point though about this point is, in many cases, if I have a non-random distribution of grains, I am going to have an impact on my formability processing. Okay, let's have a quick question then. Let's have a quick question. Steel has a typical R value equal to or greater than 1, whilst aluminium has an R value closer to 0.7. Which of these two materials would be superior for sheet metal forming of a car body panel? Explain this in terms of strain to failure. Again, try and put your answer up before we talk put your answer up on the discussion board before we talk on the web. And also, I'm sure you're going to generate lots of questions. So again, please put these questions up on the discussion board so I can get a feel for what you want to know. Okay, what other things do we need to know about basics of deformation and recrystallization textures? Well, overall, as you can imagine, deformation history is the most significant impact, i.e. if I do rolling, I will get a certain texture compared to torsion, for example. So the deformation history has a massive impact on the texture that I'm going to form. The next big impact is the crystal structure. Obviously, if I have a crystal structure that allows many crystal slip systems to operate, I will get a different texture than a crystal structure that only allows a few slip systems to operate. So for example, a face-centered cubic crystal structure in rolling will produce a different texture than a body-centered cubic crystal structure or a hexagonal close-packed structure. So whilst the deformation processing will be the same if it's rolling, the crystal structure will have an impact on where the orientations of my grains go. The other important point to note is that recrystallization sometimes has a big impact on texture. In many cases, when you have a recrystallizing grain, it has an orientation relationship with the deformed grain. So therefore, when we have a recrystallized material in a material that has already got a heavily textured material from deformation processing, we tend to get a strong recrystallization texture. Here's a good example of the impact of texture. Okay, on the middle, we have a cup that has been formed in copper that's produced effectively a no-eared surface, perfectly isotropic milling. Whereas on the left and the right-hand side, we've got scenarios where the texture has produced very heavy, large ears. Now that's quite important because, of course, that means that, of course, we're going to have to cut some of that off, because of course we can't have ears. Of course, that means we're wasting some material and we haven't got as big a cup as we possibly can. However, there's a clue here about how we can use texture. Notice on the left-hand side, our ears are occurring at 0 degrees, 90 degrees, 270, and so forth. Whereas in the other case, they're actually happening at 45 degrees to that situation. Now, what could we do? We could balance the textures of these two. Maybe if we had 50% of the orientations here with 50% of the orientations here, we would balance out this ear with this ear and so forth. And we get a situation which is much closer to isotropic. So one of the key issues about playing with texture is balancing out different textures to get the properties that we really want. I should also point out to you that we can control texture to a certain extent, and it has a big impact. Look at the two pictures on the right hand side. We have an aluminium alloy which hasn't been treated very well in terms of texture. Notice the formability is quite low, but if we can optimize the texture we can get significant levels of formability. Okay, so the key point is about understanding how texture evolves and making sure we understand how that's going to impact on subsequent processes. Okay, typically we measure texture either using X-ray diffraction or electron diffraction. X-ray diffraction is statistically better because a large volume is sampled, but we don't know the actual location of the grains. And anyway, today's electron diffraction equipment is becoming so sophisticated that we can now get data just as good using electron diffraction. And that's what we're going to say. Electron diffraction is better for studying mechanisms because one can image the same region. EBSD, electron backscatter diffraction in scanning electron microscopes, is really amazing. It makes the link between microstructure and texture, in contrast to most of the historical research on crystallographic texture. Transmission electron microscopes can also define some fine detail of texture over very small volumes of material. We can also use neutron diffraction, similar to X-ray diffraction, but the penetration in the metal is millimetres rather than microns, so it gives much bigger average volumes. The key point to note though is, for you, is that we can measure texture in many different ways with a high level of confidence. So there should be no reason why measuring texture should be an issue for you. Here is an example of the EBSD picture. In this case, we've got a picture showing lots and lots of different colours. Each of those colours represents the orientation of the grain. So you can see we've identified all the grains here, and each of those colours represents a specific orientation. So you can see here we have 15 is a certain orientation, 7 with its different colour has a different orientation. So you can see that we're looking at a set of orientations. We can actually accurately determine those orientations. One example of the need for EBSD is to investigate the relationship between deformation, texture and recrystallization. Recrystallization grains have an orientation relationship to the deformed grains, so a new texture appears. But such relationships are not precise, in contrast to those when transforming from one phase to another. So therefore we really need to understand this problem. In fact, it's one of the biggest problems we have in thermomechanical processing at the moment. Note that despite the radically different conditions under which it appears, texture development in dynamic recrystallization is very similar to static recrystallization. Okay, we'll leave it there for the time being. I know it's tough going. Don't be worried too much. Texture is a really tough subject and I'm only trying to give you a brief understanding of it, trying to get you to appreciate the impact of texture on our forming operations.